In this section of notes, we're actually going to be examining two different sections. Section 8.7 will talk about systems of linear equations and the methods for solving these systems. And we'll also touch on section 8.8, which is word problems that apply these linear systems. After completing this video, you should be able to identify a system of equations, use one of the solving methods, such as graphing, substitution, or elimination, as well as being able to use these systems of equations in applications. First, let's define what is a system of equations. So the system of equations that we'll be seeing is what we call a system of two equations or two unknowns. As you can see here, we have two equations, y equals 3x plus 4 and y equals negative 2x plus 2. A system of equations is just where you're considering more than one equation at a time. So you could have 2, 3, 4, or more equations that you need to simultaneously satisfy or simultaneously solve. So here our system is for two equations, and essentially we want to find the particular x and y values that would be satisfying not just the first equation and not just the second, but both at the same time. So how we usually think of this in an instance like this, where you have two linear equations, is that each linear equation is going to generate a graph, and that the solution to our system would be the point that those two lines share, what we think of as our intersection point. So this point is the only place where the x and y values are shared by both lines or both equations. And so that's our aim, is to go ahead and find that intersection point. Now that seems very straightforward, very simple. The issue is that graphing may not be always the best way to find those points, that it's not always straightforward to locate that position. So just as a for instance, I went ahead and graphed those two equations. So the red line that you see is 3x plus 4, the blue line is negative 2x plus 2, and here the intersection point is being identified by my graphing utility as x being negative 0.4 and y being 2.8. So for me to be able to identify that by hand without the aid of a graphing utility would be very difficult, if not impossible. So while graphing is a very clear visual way of us determining that shared point between our lines, it's not the best algebraic method because in instances where we have decimal or fractional values like we have here, it's going to be very hard to just look at those two lines and know that's where the intersection point is. So we do need other methods to assist us in those cases, and that's where our substitution and elimination methods will come into play. So before we get into our algebraic and graphing methods to solve these systems, we want to be aware that there's actually three possibilities that can occur as we solve these systems of equations. The first possibility is likely the most common one, and if you've seen systems of equations before, you've certainly seen the one solution case. So the one solution case is the one that we just saw in our last graph. That's where our two lines intersect in just one point. And the location of that point, the x and y value, that's our one solution to our system of equations. However, our lines don't necessarily have to cross at that one intersection point. So there's also the possibility that there is no solution to our system, and that would occur when your two lines are parallel. So when our lines are parallel, they never cross, they never have a shared point, and that's why there can't be any solution to our system. And then the third case, probably the most interesting one, in my opinion, is the infinite number of solutions. And that occurs when essentially your system is the same line being represented twice. And that might be obvious. You might see the same equation listed twice. A lot of times it's not obvious, though, that you have your equation given in potentially different formats, or there's been a constant multiplier occurring to your equations, and you don't see just by looking at them that they're the same equation. So what would happen is when I graph it, I would have one equation graph as a line, and then my second equation would graph as the exact same line. And so in that instance, it's really that every single point on our line is a solution. So any point I can identify as being on this shared line is technically a solution to our system. So for the infinite number of solutions case, we do want to specify what those points are. We aren't talking about every single point in the graphing plane. We're just talking about the points that lie on our line. So the typical way that we do that is we think of our solution as the set of points on our line, and we're going to let one of our variables change freely. So for instance, I could say, let's let x be some number, and then I'm going to find my equation in terms of the other variable. So if I solved this equation approximately, the line we would get is negative x minus 1. So the y-coordinate I would write in terms of that x variable. So I would describe my solution in this manner, that I could select some x number, and then the y-coordinate that would go with it that's on the line, it would be minus my x minus 1. So that's a very common way for us to represent the infinite number of solutions case. We designate this point with some unknown or to be determined value for one of our variables. So it could be x. You may also see it with a y being the placeholder here. So I could say my value is y, and then we would designate the x value that goes with it. So this would be an example where you could list your potential solutions either where x is that value to be plugged in or y is a value to be plugged in. So as we proceed through our different solving methods, we want to be aware that we could fall into any of these three categories. I could have that one solution where I get a particular x value and y value as my solution, that we have no solution because our lines are parallel, or that I am really talking about the same line twice, that every single point on my line is a solution to our system. In our first example, we're going to solve our system of equations by graphing. So what that means is I'm going to take both of these equations and put them together on the same graphing plane and look at what's occurring with my lines. Are they those parallel lines that have no solution? Are they the same line twice, indicating an infinite number of solutions? Or are they that intersection of two lines that has the solution at that intersection point? So both of these equations are not in the best format for graphing. They're in what we call our standard form. And the preferred form for graphing is typically the y-intercept or y equals mx plus b form. That just tends to be the easiest format for linear equations to generate a graph. So I'm going to go ahead and first put both of these equations into the y equals mx plus b form, and then we'll go ahead and graph our lines. So to do that, I have to solve for y, or isolate the y variable on both of these equations. So for my first equation, I'm going to subtract out my 3x to move it to the right-hand side, and then I will also divide by negative 2 to get my y variable completely by itself. So when we simplify our fractions, we get a positive 3/2 x and a negative 4 divided by 2, or 2. So that's my first line. I know some information about my line now because it's in the y equals mx plus b form. I now know the y-intercept point. So my y-intercept is that b value. So I will have a coordinate or a point at 0, negative 2. And I also now know my slope, which can help me generate more points on my line once I have one point already on there. So that's our coefficient of x, the number in front of x, which is 3/2. And then I'll go ahead and solve for the second equation here as well. So that was 2x plus y equals 5. To get this into the slope-intercept form, again, we'll solve for y. So I need to subtract my 2x quantity to move it to the right side. And that actually is enough to get it into mx plus b. So again, looking at each piece of it, the y-intercept would be at 0, 5, because our b value is 5. And then the slope, which is the number in front of my x variable, that's negative 2. Or if you prefer to think of it as a fraction, for when we do rise over run, it's negative 2 over 1. So now that I have both of these lines, I can go ahead and generate my graph. However, one thing to think about when you are graphing by hand is you need to write the scale. So both of my lines don't really have very large values in terms of the y-intercepts, and I don't foresee needing very large values either for x or for y. So I'm going to go ahead and kind of count by the traditional scaling, which is where every tick mark counts as 1, but I need to label that on my graph. If I leave my graph without labels, then that's not clear what the scale actually is, and that would be very misleading to whoever reads my graph. So I'm going to let each tick mark represent as 1, and I could go through and label every tick mark as a 1, but I don't really like the way that looks because the numbers tend to get pretty cluttered together. So I kind of like to allow every other tick mark or skipping some tick marks and just labeling those just to allow for a little less clutter on the graph. So I counted by every other tick mark, but if you go back and look, each individual tick mark would be 1 since I skipped every other one. And we need to label not just the positive direction on our axes, but also the negative direction. And I'm going to do the same thing for y, because you can technically have different scales for your x and your y axis. And that can happen very commonly when your y values get very large. So your x values don't necessarily get large, but the y's do. In instances like that, it's helpful to change your scale and maybe count every tick mark by a larger number for y. Here, I don't foresee that as being an issue, so we'll just keep the same scale of each tick mark counting as a 1. Now I'm going to graph the first line that we had, the 3/2 x minus 2. The y-intercept was at -2. And then my slope can help me find the next point on my line. So one of the ways that we think about slope is it's the rise divided by the run. And the rise, that describes how my line is changing vertically, how my points are traveling both up or down. And then the run is movement from the left to the right. So this 3 that I see, it's actually a positive 3. That's going to relate to movement up 3 on my line. And then the positive 2 that I see in the denominator would move my point horizontally in a positive direction, which is to the right 2 units. So it's essentially a description how to get from one point to the next on your line. So I can travel up 3 and right 2 from my y-intercept point. So 1, 2, 3, up to the right would be the next location of my point. And that's technically enough to graph your line. You know, I'd maybe just use a ruler and generate my straight line here. The issue, though, with solving systems by graphing is that we need very exact graphs. That if we were to draw our line a little bit askew and then looked at our intersection point, that could really throw things off. So this would be an instance where we want to be very exact when doing our graphs and get as accurate of lines as we can. So to do that, a very helpful way is to generate as many points on the graphing plane as you can. So I'm not going to allow just for those 2 points. I'm going to get all the points that I can that will fit on this graph. So I'm going to continue using my slope, going up 1, 2, 3, and to the right 2, there's another point. Up 1, 2, 3, to the right 2, there's another. Up 1, 2, 3, and right 2. So I've covered all my points on my line, kind of going up towards the right on my graph, but I still have this whole section to the left that I don't have points for. So the good news is you can find those points, you just reverse the direction that you found for rise and run. So what I mean by that is rather than going up 3, I could reverse that. I could go down 3 units, but then to compensate, I have to also reverse the run piece. So rather than going right, I would go left 2. So I would go down 1, 2, 3, to the left 2, and that fits with how our line was sloping. We can see it's still going through the same kind of slope and direction that we saw previously. And again, I can generate as many points as I want. 1, 2, 3 down, to the left, and I've got as many points as I can. So at this point, I would use a ruler or a straight edge to make this line as perfect as I can. Alright, so I've generated my straight line through those points. And then when you do make your straight line, remember to put your never-ending arrows at each end so that you know that your line will continue forever in both directions. Alright, so there is our first line. Now we want to graph our second line on the exact same graphing plane so we can see where our lines lie with respect to each other. So my y-intercept was 5, positive 5. So I'm going to graph that first. And then I can use my slope as rise over run. Now this time we do have a negative. And we want to decide where we want that negative to go. So right now it's on my numerator. So that would mean that I need to go down 2 units for every 1 on my run, which would be movement to the right 1. And I could also potentially change this. I could let my negative go on the bottom of my rise over run. And that would be essentially kind of like the reverse process that we saw previously. That would allow me to go up 2 for my rise, but then we have to compensate by going to the left 1 on the run. So we can use both of those to essentially generate all the points on my line. So first let's do the down 2 and right 1. So down 2 units and then right 1. Down 2 units, right 1. And this point right here is on my other line. So that right there is actually a very helpful point. That's our intersection point that we're going to have. So that's very neat that I found that already. So I'm just going to do a couple more points to finish off this line, but there's our solution point. We can see that that's where our 2 lines are going to cross each other. So again, go down 2, right 1, down 2, right 1. And since I was fortunate enough to already get my intersection point, I don't necessarily have to be quite as careful on graphing this line as I had my previous one. But let's show our straight line and then we'll write our solution point. So there is my straight line with arrows on each end. And then I would look at the intersection, that point that I found just a short while ago, where our 2 lines both share that same point. That's going to be our solution. So my solution point is here, and we want to look at the x and the y coordinate. So my x coordinate for that point is at 2, and then the y coordinate is 1. So that is my solution to this system. That would be when x is that value of 2 and y is the value of 1. So there's 2 ways to write your solution. You could write it as that coordinate form. Alternatively, you could state what the x and the y values are. So that's when x equals 2 and when y equals 1. So both of those would be acceptable ways potentially to write our solution. And that's it. That's how you would solve your system by graphing. You would need to do whatever work needed to get your equation formats into a format that you can graph. So if they're already written in y equals mx plus b form, great. You can kind of use your slope and y-intercept to graph your line like we did here. Or there's other methods to graph as well, such as making a table and graphing a table of points, or finding x and y-intercepts and using those to graph. So using one of those graphing methods, we want to generate these 2 lines and then look for that intersection point for the one solution. Now, as I mentioned previously, graphing is not the only method we use to solve systems of equations, because there are some faults in it. So one fault would be if I'm not very careful in graphing my lines, I could identify an intersection location that's actually not correct. So that's one problem. And the second problem is really the big one, and that's we got lucky in this instance because our x and y value were whole numbers that we could easily see off of our graph. However, in a lot of cases, that's not going to happen. You're going to get an intersection point that doesn't fall perfectly on a tick mark, and you can't easily read off of your graph. And that's where we need these other algebraic methods to assist us in finding our solution to the system. So that's our graphing method, and we have 2 algebraic methods. So the first one we're going to look at is called the substitution method, and I've listed out the 5 steps that you would go through to solve the system of equations using substitution. And we'll detail these 5 steps as we go through our examples as well. So the first step is you're going to take one of your equations and you're going to solve for one of the variables, either the x or the y, essentially just isolating your variable so it's in the format x equals or y equals. The second step is to take that equation that you just solved in step 1 and substitute it into the other equation to take on the role of that other variable. And that step is the important one because that's going to allow us to take this system that has two variables and two equations and get it into one equation with just a single variable. And that allows us to really solve it then. So once I've substituted, then we can solve that equation that has the single variable in it, get it down to find the value of that particular variable, and then once we have it, we can go back to one of our original equations and plug in that value for our variable to find the value for the other variable. And then the last step would be to write our solution either in the x equals or y equals form or as a point, and also to check it. That's one of the things that we haven't talked about thus far, but we can check this system of equations. And so we'll look at how to do that here in a moment. So let's start this process, and I'll label it very explicitly as we go through here in case you're not familiar with going through this substitution method. But you don't have to label your steps as you go through them on your own. Ideally, you would know this algebraic method well enough that you would just know what comes next. So the first step is we need to solve for a variable. And here you can be very strategic in picking which equation and which variable may generate the less work for you, or perhaps maybe avoid fractions and things like that. So between my two equations, the easiest variable I think to solve for would be this first equation, 2x minus y equals 13, and solving for y on that I think would be the easiest choice here. And that's how I know that, and making that choice is because looking at my equation, I can very easily get y by itself. I just need to move the 2x term. And I also don't have any numerical coefficient for y, it's just a 1. And that also tends to be a good choice because then you can avoid things like fractions. Alright, so solving for y then, we would go ahead and move this 2x term to the other side of my equation. So I would subtract it. That would leave me with negative y equals negative 2x plus 13. And I don't really have y isolated because of that negative. So I can go ahead and divide out a negative 1 or multiply a negative 1, or think of it as changing all the signs on your equation just to make my y positive. So it would become a positive y, my negative 2 would go into a positive 2, and my 13 would go to a negative 13. So there is step 1 completed. We have solved one of our equations for one of the variables. So I solved the first equation for the value of y. So now we get to move into step 2. And step 2 is where we need to do that substitution step. And the important thing here on this step is that we always substitute it into the other equation, the equation that we haven't done any manipulation on. So here, this is the second equation, negative 4x minus 9y equals 7. And I'm going to replace the y variable, because that's the variable that I solved for in step 1. So wherever I see that y in my equation, I'm going to replace it with what we know it's equivalent to, which is the 2x minus 13. And if you look at this equation that I've generated by doing that substitution step, now I don't have x and y, I have only x. And that's important. That's what's going to allow me to go ahead and solve for the value of x here. So to solve, we would first reduce down this equation so I can distribute my negative 9. 9 times 2 gets me 18x. The negative 9 times the negative 13 is going to be positive 117 here, and then equals 7. And I can also combine like terms and keep going from there. So actually, I kind of already started on step 3. So I'll actually kind of put this last step I did as step 3 here. And that's very common when you get used to doing this process. You already know what's coming next, and you can very kind of automatically shift to it. So step 3 is to solve. So I've already started kind of solving for the variable that we substituted in. So solving, we're looking for isolating x, so I can combine the 4 and the negative 18. That's negative 22x plus 117 equals 7. and then we need to move our values to get the x by itself. So I can subtract 117, and I get negative 22x equals negative 110. Divide out the negative 22, and we have our solution that x is going to equal 5 here when you do the division 110 divided by 22. Now I'm not done in my solving process. If you notice, we've only gone to step 3. We still have to find the other variable. So that's going to get us to step 4 here. So step 4 in our process is to find the other variable. So here I need, in this case, to find the value of y, because I had solved for x in the previous step. So I can go back to either of my two original equations to solve for the value of y. I could also use potentially the equation that we found in step 1, that y equals 2x minus 13. Those all relate to x and y. My preference is to go back to one of the original two equations when I get into step 4 here. And why that is because with any algebraic method, we can make mistakes, right? We can accidentally do some of our math wrong and not realize it. So I like to do this step 4 in one of the original equations, so that if my value of x was wrong, say maybe I made my mistake in this first step here, it kind of allows us a chance to catch that when I plug in my x value and back into the original, I may get a very strange y value, and that's an indicator that there could be something wrong with our solving process. So I kind of prefer going back to the original two equations, but you could have just as easily used the y equals 2x minus 13. Either way, how that would work is you're going to now substitute in the value that you found for x here. So x was 5. And then get your y value. So this is 10 minus y equals 13. This time, let me go ahead and do something different. I'll add the y. Get 10 equals 13 plus y. And then subtract the 13 over. And so y equals negative 3. And that's our other solution. That's the value for y. So then the last step, what we think of as step 5 here, that's to write your solution. So we need to write the solution together with x and y. So there's two ways to do that. There's our ordered pair that we saw. So x is 5, y is negative 3. Or you could also write it out as x equaling 5 and y equals negative 3. So that's our solution to our system. Now here, also in step 5, they also suggest for us to check our answer. And that's the nice thing about these algebraic methods as well, is they allow us to go ahead and check, right? Did I actually find the correct solution or not? And I really highly suggest doing a check for any sort of equation, not just using the systems of equations, because it lets you know that you got the correct answer, right? And when we're doing things that could be high stakes, like I'm taking an exam, that check step is crucial, because we tend to make silly mistakes when we're under time constraints like an exam. So how would a check look? Well, my check would be going back to the original two equations, and it has to be the original equations that were given to you. You don't want to use anything that has been manipulated, because we could have made our mistake in that manipulation. So going back to my original two equations, I'm going to plug in the value for x and y that we found, and then just see, do my equations balance? Are the left-hand sides and right-hand sides equaling the same quantities? So I would go in, put in my x value as 5 and the y value of negative 3, and then we can check our values. And this check step, you really only have to write it out if that's requested, right? If in the solving process it says solve and check. if it doesn't ask specifically for that step, this is something that you could do in your head or potentially just type in quickly to your calculator and make sure that it checks out. So the first equation works. I got 13 equals 13. But here's the thing, though. That's not enough to actually know that this is true because both have to be satisfied. And when you're dealing with the substitution method or solving systems of equations, one of your equations is always going to verify, using these steps. If I had made a mistake and then found my other variable based off that mistake, one of these would verify, would check. So we do have to check both. They both have to be true. And in this instance, they are. So we know for sure that our solution, x equaling 5 and y equaling -3, is correct. In example 3, we'll go ahead and solve another system of equations using substitution. Just getting more practice in going through those steps. So here we can see we have our two equations. So step 1 would be to pick one of those equations and to solve for a particular variable. And this time around, it's not maybe as obvious which choice would be the easiest one. So when I compare equation 1 and 2, what I can see is my coefficients on the first equation are smaller than on the second equation. So that's a good motivator for me to perhaps use the top equation, just because our coefficients are smaller. And when we do operations with small numbers, it tends to be nice. So I'm going to take this first equation, and then we have to choose, do we solve for x or solve for y? And they're both going to generate some fractional values for us when we solve. So it doesn't matter as much which one we pick. I think I'll go ahead and pick the y value this time just because I'd be dividing by 2. And I like fractions in terms of halves a little bit better than thirds that I would eventually see if I solve for x. So you could have also picked x, but I'm just trying to get as easy or nice of values as we can. So if I decide to choose to solve for y, then I'm going to go ahead and move my 3x to the other side of my equation, and then we would divide by -2 on each side. And I get 3 equals 3 halves x. My two negatives would also divide, become a +2. All right, and that would lead us into step 2 of our solving process, which is that substitution step. So step 2 is to substitute our equation into the other equation. So my other equation here was the -9x plus 6y equals -1. And where I see my y value, that's going to be replaced by the equation that we just found. So that was 3 halves x plus 2. And that's the end of step 2. Step 3 is now to solve for the x in this instance. So solving for the variable that you have just created as your only variable in your equation. So I can do that by distributing our 6. So 6 times 3 halves, that would be 18 over 2 or 9x. And 6 times 2 gets me a 12, a +12. And then something very interesting happens here. When we combine like terms for my x value, the -9x and the +9x, those add to 0. So this is actually 0 x's, so to speak. So my variable x dropped out. It's not there anymore. And I'm left with 12 equals -1. And so this is kind of strange compared to what we did last, but it could happen. And this is actually an indicator that we have a special case, one of those other solution possibilities, right? We don't have the one solution case anymore. It could be the no solution or the infinitely many. So here our variable dropped out, right? The variable canceled out. And what we were left with is a false equality, right? 12 does not equal that -1. Oops, equality. And so that's telling me what's going on with our system here, really. And actually, we've seen this before when we were solving normal linear equations. You could have your x variable drop out and you get a false equality. In both instances, it means the same thing. This false equality means that we have no solution. There's no x and y value that would satisfy both of our equations in this system. And we would leave it there. We would call it no solution. Or if you're thinking of these as sets of solutions, that's the empty set or the set of nothing inside, which we use that circle with a line through it to symbolize the empty set. And that would be it. So kind of be aware that you could have those other two solution possibilities come up. Right? You could get that one solution xy. You could also get the no solution case or the infinitely many case. So the other algebraic method that we want to know is the elimination method. And part of the reason why we have all these different methods to solve systems of equations is that systems of equations are actually very useful, that they come across a lot in a bunch of different applications. And because of that, not all solution methods are going to be maybe the best choice or the easiest way to solve the system. So kind of like how graphing is not the best way to find a solution if your solution has decimals or fractional values for x and y. The same can be said of the substitution method, that sometimes when using the substitution method, our math can get very messy with a bunch of fractions in there, and it becomes very cumbersome to do that substitution method. So the elimination method is nice because it takes away or allows us to find things in a different way than the substitution method. And just to point it out as well, the elimination method is highly successful when you have more than two unknowns in two equations. So that's all that we're going to be looking for here is equations with x and y, but you could have more variables. I could have x, y, and z, 3 variables. I could have 4 variables, 5 variables. For those larger, what we call larger systems of equations, so I have more than 2 unknowns, I have 3, 4, 5 unknowns that we're looking to satisfy or solve for. That's where the elimination method is very, very good and very, very successful. So what are the steps of our elimination method? So first, we're going to write both of our equations in the standard form. So we want the x and the y on the left-hand side and your constant on the right-hand side. And ideally there won't be any fractional values there if it's true standard form. Then what we're going to do is make sure that our coefficients for one of the variables, either just x or just y, are going to be negative values or opposites of each other. All right, so what do I mean by that? I mean, if we look at our example here, I have 4x and 3x, 3y and 2y. I want these to be the same coefficient number, but one's positive and one's negative. So for instance, I could make 4 and 3 into a value of 12 by multiplying 4 by 3 and by multiplying 3 by 4. And I'd want one of these to be a positive 12 and one of these to be a negative 12. Or, similarly, I could make both my y's have the same coefficient value of 6 by multiplying the top equation by 2 and the bottom equation by 3. So that's what we want to do to allow our elimination method to go smoothly. We want to multiply one or both of our equations by whatever number we need so that the coefficients would have the same value, but one would be positive and one would be negative. And once we have that, step 3 is we're going to add those two equations, and that's where we're going to see one of our variables add to 0. And that's kind of the point of step 2 there was to get that variables so that when you added your two equations, they would add to 0. And then when that happens, you now have an equation with just one variable in it because one of your variables added to 0. So step 4, you could solve it, and essentially the last several steps are just like our elimination method. Once you solve for one variable, you can substitute back in to one of your original equations to find the other variable, and then we write out our solution set and check it. So let's try out our elimination method here. So step 1 is to get one of the coefficients to be opposites of each other. So one set of coefficients to be opposites. And again, we have choice on this. We could choose either x or y. And I kind of like getting the y values to be the same here, just because our numbers will be a little bit smaller. Rather than getting a shared value of 12, I could get a shared value of 6. So how do I do that? I'm going to multiply each of my equations by some value. So to get the hope here is I get a 6y, right, from both of these. So on the first equation I'd multiply by a 2, and the second equation we would multiply by a 3. Now that would get both of my coefficients for y to be the value of 6, but we want opposites, one to be positive, one to be negative. So I need to make one of these into a negative value, so when it multiplies through I'll get a negative coefficient. And it doesn't matter which one you pick, I'll just let my 3 be negative this time. And let's see what the result would be. So when I multiply that, we're going to multiply each and every part of our equation by the number we selected. So kind of like distributing. 2 times 4x is 8x. 2 times 3 is that 6x that we want, or 6y that we wanted. And then I also have to multiply the right-hand side. So don't forget to multiply the right-hand side of your equation to keep it balanced. So the 1 multiplied by the value of 2 is going to get me a 2. And then same idea for the second equation, multiply through your negative 3. 3 times negative 3 is negative 9x. 3 times our 2, this will be a negative 6y. And then 1 times, or that's not a 1, pardon me, that was a 2 there. If I look back at my original equation. So be careful, that's a very common thing I find, especially for myself, is when we're writing down our system of equations, we may accidentally write down the wrong number. So watch for that. It's a really common mistake. So that was a 2, so 3 times my 2, this would be a negative 6. So that's still the same system of equations. All that we have done is gone through and gotten our coefficients to be opposites of each other. And actually, if I look back at my steps here, that was technically step 2, not step 1. That's because step 1 was already done for us. So step 1 was to get them into the standard form. And this one already was, right? Both equations were already in the standard form. So that's why I kind of skipped that step, because they were already in the format that we wanted. So step 1 was get it in the standard form. Step 2 was to get the coefficients to be opposites. And now we can continue into step 3 now. And that's to add the 2 equations that we just found. Okay, so we had 8x plus 6y equals 2. Negative 9x minus 6y equals negative 6. So we're going to add those equations. And what we mean by add them is you're just adding up the like values. And this is why we wanted those in standard form, by the way, is so that our x's and y's and constants were all placed in the same location column-wise. So 8x added with a negative 9x is a negative 1x. 6y added with negative 6y is 0y. That's what we wanted to have happen, to have those variables cancel out. And 2 added with negative 6 is a negative 4. And so when it's all said and done, I have negative 1x equals negative 4. And that will lead us into step 4 now, which is to solve the equation that you got by adding your equations. So to solve, I really just need to divide out or deal with that negative that's in front of my x value. So I could divide out negative 1, and I get that x equals positive 4. Alright, so I found my x value, but I'm not done. I have to find the y value now. So that's going to lead us into step 5, which is to find the other variable, to solve for the other variable. So in this instance, that's y that we need to solve for. So I can go back to either of my 2 original equations. It doesn't matter which one. So again, you can select maybe based off of which one you think is going to be easier to use. So I actually use the second one, 3x plus 2y equals 2. And we replace the value that we got for x. And so when I replace that, we get 3 times 4, which is 12, plus 2y equals 2. We will subtract the value of 12 to solve for y and get y by itself. So 2y equals negative 10. Divide out the value of 2, and y is negative 5. Alright, so we have technically our solution. However, we need to write it out formally and also check it. So that's our step 6. This is our writing the solution, and then we'll check it as well. So the solution that we found written in the coordinate form is 4, negative 5. Or again, depending upon your situation, maybe it's okay to write it in the other format, which is x equals 4 and y equals negative 5. So there's our solution. And now we want to go ahead and also check it, just to be sure that we didn't have any silly mistakes happen, and that we actually did find the correct values for our solution. And so the check step is the same as what we saw for the substitution, that to check it, you're going to put it back into the original two equations. So I have 4x plus 3y equals 1 that we need to check it into, and 3x plus 2y equals 2. So what we're going to do is replace the x and y value and see if our equations balance for us. Alright, so replacing in, x is 4, y is negative 5. We'll see what we get there. So 4 times 4, that's 16. And 3 times my negative 5 is negative 15. So there we can see it balances for the first equation. I get 1 equals 1. And we still have to check the second one. So I get 3 times 4, which is 12. 2 times my negative 5, which is negative 10. And it also verifies 2 equals 2. So we know that we definitely found the correct solution to our system. Alright, in example 5, we'll try elimination one more time with a different system of equations to make sure we feel comfortable with our elimination method as well. So step 1 again is making sure that our equations are in the standard form, which they are. So that's done for us. Step 2 is to get those coefficients to be opposites. And we can choose whichever variable we want, either x or y. I kind of like the value of perhaps the y here, because I can see how I can make my negative 2 into a negative 4 pretty easily. I just need to multiply the top equation by 2 to do that. But you could also have picked x as well. It doesn't really matter. The method, if you did pick a different variable to eliminate in this step, you'd still find the same solution when you get to the end of the process. So don't feel like if you chose a different variable than I chose that you'd get something different. You'd still solve and get the same result. So I'm going to take the top equation here, and I said I want to multiply it by 2. And you don't have to multiply both equations like we saw in our last example. Sometimes you only need to multiply one to get one of your coefficients to be opposites. And that's actually kind of the nice case. There's less work to do when you're only multiplying one. So then distributing our 2 through, we would get 3 times 2, which is 6x. 2 times our negative 2 is a negative 4y. And then 4 needs to multiply by 2 as well and get me an 8. And then I actually didn't want to change anything to my second equation, so I'm just going to write him down again. So there's our step 2, and then step 3 is to add the equations. So I'm going to just rewrite my equations again, and we'll show the addition step. Okay, so add our equations together, and 6x combined with a negative 6x is 0x, negative 4y combined with 4y is 0y, and 8 combined with a negative 8 is 0. And this is, again, kind of strange, because what happened was, I was trying to get the y's to add to 0, but my x's actually added to 0 as well. So what I ended up getting was 0 on my left-hand side of the equation and 0 on the right-hand side of the equation. So this is, again, strange, and it's also an indicator that we're falling into the no solution or infinitely many solutions possibilities. And you may have even noticed back on step 2 that the coefficients would have added to 0 for x and for y. We still need to actually perform the addition in step 3 though, so that we could figure out the sort of result. Did I get a true equality or not? So in this instance, the variables canceled out. But we were left with a true equality, right? 0 does in fact equal 0 here. So this isn't the no solution case. The no solution case was when it's false, right? I get two things that aren't actually equal. Here, I got that it was true, right? These two things are equal. And what that's indicating to me is that this is the infinite number of solutions case. However, that's not actually my answer. I'm just classifying how many solutions there are, right? There's an infinite number of points lying essentially on this line. This is essentially the same line in two different maybe formats that we're seeing. And every point on that line is a solution. So my answer is not infinite number of solutions. I have to actually detail what that solution is. I want to write this out, right? I want to write my solution as some coordinate on my line, right? Where I choose either x is going to be my variable that can take on anything, or the y. So let's say I let x be the variable, right? Then I need to fill in my y coordinate with what that y would be in terms of x. So how we do that is you're going to take one of your equations and you're going to solve it for that variable. So I'm going to solve one equation for a particular variable. So in this instance, for y. So it doesn't matter which one. I think I'll take the second equation this time around. So negative 6x plus 4y equals negative 8. I'm going to solve that for y, or isolate my y variable. So I can add the 6x over, and I'd be left with 4y equals 6x minus 8. I think that looked more like a 6 there. And then I got to divide by 4. So I get y equals 6 divided by 4, which we can reduce to 3 over 2x, and 8 divided by 4, which is 2. So that's going to be what I plug in to my point form here. Instead of the y, I'm going to write 3/2 x minus 2. And that's just one way to write our solution. Again, we could have written the point the other way, where y was the value that could take on anything it wants, and then the x coordinate would be written in terms of y. However, since x tends to be our independent variable, the variable that we plug in, that tends to be the format that we tend to see most often in this infinite number of solutions case. So there is my systems of equations there, or my solution to my system. That x could be any particular value, and once we decide it, the y value would be 3/2 of that x value, take away 2. All right, Examples 6 and 7 are going to talk about applications to our systems of equations. And there's really two different formats that we'll see. So example 6 is an example where they're detailing what our equations are in our problem setup. We don't really have to work so hard to generate our equations. They're going to describe them for us. So a particular field has a perimeter of 320 yards. Its length measures 40 yards more than its width, and we want to know the dimensions of the field. So this one actually has a little bit of hidden context. When we talk about a field, we're talking about a particular shape, and it may not be obvious without thinking about a little bit what shape they're describing. So a field, if you think of sports like football and soccer and all those different sports, they tend to have fields that are rectangular. There are, exceptions, of course, like baseball, is not a rectangular field per se. But I have evidence that it's going to be a rectangle as well because they talked about length and width. That length and width only makes sense when you have a rectangle. So we're describing, honestly, a rectangle here. And they told us some information about the length and the width, and some other information as well. So what are we going to do to solve this? Well, if we think of this in terms of steps, step 1 is we want to write the system of equations. All right, so how am I going to do that? Well, let's understand the information they gave me in my problem. It says it has a perimeter, our field has a perimeter of 320 yards. And that the length of my field measures 4 yards more than the width. So if my width is some value w, the length would be that same w, but the 40 yards more, so we'd add the 40 yards. So I already generated kind of one equation with this length that we created. So that will be one of our equations. But I also need to include information on the perimeter. Well, I'm lucky because squares do have specific formulas for the perimeter. So I could Google or look up the perimeter formula for a rectangle, and squares are the same thing as well. Perimeter is 2 lengths added with 2 widths. And I do know the perimeter is 320. So the perimeter equation would be one of my equations in my system, and then the length equation that they described would be my second equation. And for our purposes, we're going to be doing systems with 2 variables, and so we're expecting 2 equations. So there is my system. 320 equals 2 times the length plus 2 times the width, and I know that the length is equal to the width plus 40. Now once I have my systems of equations, what do I do next? Well, we're going to solve the system that we found. And we can do that with any of our methods. I could use it by graphing, by using substitution, or by using elimination. And here, once you've done all 3, you can start being knowledgeable in which one might make the most sense or might be the easiest path to go through. When I look at my system of equations, I can see that my second equation is solved in terms of W or in terms of L already. So that makes sense for me to use substitution. However, you don't have to use that. You could have used graphing, or you could have used elimination. But from my viewpoint, it's kind of already set up to easily use substitution. So if I do choose that substitution method, then I would take one of my equations and substitute my other equation inside. So here, since L was already solved for, that can replace the value of L for us. So L was the width plus 40. And now that I have that substituted, we can go ahead and solve for our W. So distributing 2, that's 2W plus 80 plus 2W. We can combine the like terms of the 2 W's to create 4W. And then I need to subtract my 80. And I'd be left with 240 equals 4W. Divide out 4. and I get that my width W is 60. Now my system is not actually solved. All that I have found is the W variable. We have to go back and find the other variable. So I can use either of my two original equations. When I compare them, the second one definitely is going to be the easier way to find the length. So I'm going to take my equation and replace the W that we just found, which was 60, and that would leave me with the length being 100. So I found my variables, my width for 60 and my length for 100. And then, I could definitely check this as well. I could go back to my original two equations, plug in the length value for 100 and the width value for 60, and make sure that they both yield true equations. So, that might be something to kind of do in your head or in a calculator to verify that that works. And then step 3 for these applications, I would say, is to put your answer in the context of your problem. So I find that if I state the answer as a sentence, that I'm going to remember to state what each variable was, and then also what units went with each variable. So I find that just, when you put it in that sentence format, you automatically remember to do those two things, because that's what we need, right? We have two separate solutions and with units associated. So they asked for the dimensions in this problem, so I could say the dimensions of the field are, and then here we would state the width and the length. So the width was 60, and if we wondered what we were measuring 60 in, they were describing in the original problem things in terms of yards. So this is 60 yards. By my other dimension, which is the length, that was 100 yards. So I think it's a very good habit or practice to get into when you're dealing with word problems like this, to always state your answer in a complete sentence, because then when you do that, you're forced to put it back in the context of the problem, and you're going to remember to include all your answers with units, which is important. All right, and that brings us to our last example, example 7. And this is an instance where our equations are going to require more work from us to generate them. So we'll look at that here in a second. So a store sells cashews for $5 per pound and peanuts for $2.50 per pound. The manager decides to mix 30 pounds of peanuts with some cashews and sell the mixture for $3 per pound. How many pounds of cashews should be mixed with the peanuts so that the mixture will produce the same revenue as selling the peanuts separately? So here, we aren't being necessarily given equations as directly as we did in our last example. And there's a lot of things going on. They have things being stated in terms of cashews and peanuts and a mixture that we're going to create. And that means that there's going to be more complicated math kind of happening. Now the good news is we've actually done some of these problems in the past. These are sometimes referred to as mixture problems, and we saw them in section 7.2. And the trick and strategy that we learned to generate our equations were to make tables. That if we can organize all this information in a table, it's going to become a lot more clear what math we have to do to generate our equations. So again, we're going through that same 3-step process. So step 1 is to write the system of equations. And so here to write our system of equations, we'll actually first start by organizing our information into a table. And part of how I knew that this was going to need a table to help generate our equations is because we have these different categories. So I have the category of cashews, peanuts, and also that we're creating a mixture between these two. And the mixture is also kind of, in other instances, thought of as the total, right? You're combining these cashews and peanuts to create this new total mixture as an end result. So we have the different categories, which is a hint that we need a table. And we're also talking about these categories with respect to different things. So they talked about the cost per pound. So reading through, the cashews cost $5 per pound, the peanuts cost $2.50 per pound, and we want to sell the mixture for $3 per pound. So we have the cost per pound that we're including, but we're also including a quantity here of how many pounds we're going to use of all the different nuts. So we did find out that we're going to mix 30 pounds of peanuts, so we have 30 pounds of peanuts, with some amount of cashews to create our mixture. And they didn't tell me how many cashews or pounds of cashews we're going to be using. They also didn't specify the mixture, so those may be things that we need to determine. And they were also interested in revenue, right? They want to have the same revenue, you know, for selling the mixture as we did if we had sold these separately. So there's also this category of revenue that we care about. And we want this mixture, that amount, to be equal to the two categories, cashews and peanuts, to be equal to the revenue from the mixture when we get done. So all that I've done is taken my word problem and I've broken it into this table. I've rewritten in all of our information into the table form. And any blank values in our table indicate values that we either need to calculate or could represent variables for us. So what I can do is first look at the quantity amount. So I don't know the amount of cashews that we're selling, so that could be a variable. I'm going to call it C for cashews here. I also don't know how much of the mixture we end up with, so I'm going to call that M for mixture. And then revenue, how we find the revenue is you take your cost per pound and you multiply it by the quantity of pounds. And that's really common when we're doing this kind of table-based equation forming, that you're going to multiply your two columns to generate a third column. So my cost 5 times the quantity C would yield a revenue 5 times C for our cashews. For the peanuts, I would do 250 times 30. And we could calculate that value. It's actually 75 there. And we do 250 times 30. And then 3 times M to represent the revenue for the mixture. And they described how these values are related, that we want the revenue of what I get from cashews and peanuts for that to total and equal the value that I get for the revenue for my mixture. So that's going to be one of my systems of equations right there. That 5C plus the 250 times 30, or 75, must equal 3M. So that equation came from the revenue, but a system of equations like this one requires 2 equations because I have 2 variables. And that second equation is actually going to come from our quantity, that we know how our quantities are related, that I'm mixing together my cashews and my peanuts to create our mixture total. So the mixture is the amount of cashews added with the 30 pounds of our peanuts. So that's where our second equation comes from, is that we do know how those quantities are going to relate to each other. So there is our system of equations. And now we can go through the second step, which is to solve that system. And the method that you use, again, you could use graphing, substitution, or elimination. In this instance, I think substitution will probably work well, again, because I have one of my equations already isolated for one of the variables. So I already have M solved for, and that would make substitution kind of an easy process. But you don't have to always use substitution, right? You could use elimination or graphing as well. So if I decide to use substitution, I'm going to take this first equation and replace the M, and that's because my second equation already has M by itself. So M is C plus 30. So now that I've performed that substitution, my equation is just in terms of C, so we can go ahead and solve it. So 5C plus 75 would equal, we distribute our 3C plus 30. I need to isolate my variable C, so I can subtract the 3C to get 2C plus 75 equals 30. Subtract the 75 and get that 2C equals, oops, I messed up there, sorry. I just realized it. We shouldn't get a negative quantity. So I forgot to distribute my 3 times 30. This is a 90 right there, actually. So let me fix that. Yeah, here it wouldn't make sense to have a negative quantity of cashews. So that's how I know I made a mistake there. So 90 minus 75, that's 15. Positive 15 makes a lot more sense. And then divide by 2. And so our quantity C is 15 divided by 2, or 7.5. And now that I found C, we can go back and find our other variable. So I'm going to just use the C plus 30 equals M equation and replace that C with the 7.5 that we found. So that would get me 37.5 equals the M. Okay, so that's step 2. Step 3, once we've solved the system, is to write our solution as a sentence. And that, again, is just to get our 2 values put in the context of the problem and with the appropriate units on them. So we had that C was 7.5 and M was 37.5. Here I picked meaningful letters, so I know C represents the pounds of cashews and M represents the pounds in our mixture. If you picked variables that you weren't sure what the values actually represented, you could go back to your table and look at what you were talking about. Right? We were talking about quantity of cashews and quantity of the mixture. So the mixture will require 7.5 pounds of cashews. And let me look back at our original statement. I think that's all they asked about, right? How many pounds of cashews should be mixed? Yeah, so even though we found the mixture value M to be 37.5, they actually weren't interested in finding that number. They just wanted to know the amount of cashews. So I could end it there. If you did want to include both, the value for C and the value for M, you could say something like the 37.5 pound mixture would require 7.5 pounds of cashews.